So the next topic we want to look at is figuring out strategies for balancing oxidation reduction equations. So remember, whenever we have an oxidation reaction, it's got to be paired with a reduction reaction, and we call them each half reaction. So I'd have an oxidation half reaction and a reduction half reaction. And our understanding is that these reactions are coupled together. And what we mean by that is the electrons that are flowing out of the oxidation reaction. Remember, oxidation is loss, so those electrons are being released. So those electrons that are being lost from the oxidation reaction, they're being consumed in the reduction reaction. So in that way, the reactions are coupled together. So when we're balancing, what we want to ensure is that the electron flow out of the oxidation matches the electron flow into the reduction. So we're going to want the electrons out from the reduction to equal the electrons out from the oxidation to equal the electrons in for the reduction. So that's what we're trying to keep track of. So what we'll do is we'll balance the two half reactions separately. That's the way we want to approach it, and then combine them together in the final step. So we call this the half reaction method. And we want to assign oxidation numbers to everything to kind of figure out what's going on. You don't have to do that step, but generally speaking, it makes it easier to make sense of everything else you want to do, and then write them out as two half reactions. You're going to split things up from the original overall reaction to a half reaction. Then you're going to balance, and balancing is going to be done in a series of very specific steps, and so that's what we want to pay attention to. So first you're going to want to identify everything other than hydrogen and oxygen and balance that. Then you're going to balance the oxygen by adding water molecules to the side that's oxygen deficient. And then once you've done that, then you'll have made the hydrogen unbalanced. So you'll balance hydrogen by adding H plus ions to the side that is hydrogen deficient. Technically, this means that we're balancing under acidic conditions. That's what we'll start with, but later on we can talk about how we would balance things under basic conditions. So keep in mind all of this oxidation reduction chemistry. This is what happens within batteries. So it turns out something like a car battery runs under acidic conditions, but something like a household battery, like a AAA battery or a 9-volt battery, anything like that, it runs under basic conditions. Okay, so let's see. Once you've balanced all the atoms, you'll kind of by default have unbalanced the charges even more. And now what you're going to do is balance by adding electrons in. And so here it says balance charge by adding electrons. So remember, since I'm adding in negative charges, I'm going to be adding into the side that's more positive to make the electron count or the overall charge equal. The last step here, number 4, it says multiply the half reactions by integers so that the electrons gained and lost are the same. So we want to make sure that the electron flow is equal in both sides. Okay, add the half reactions together, subtracting things that appear on both sides. So we're just simplifying. And then 6 and 7 are basically verifying that everything looks okay. So make sure that it's balanced according to mass. Really, that means that the atom count is the same on both sides. And then 7, make sure the equation is balanced according to charge. So for that, you're going to calculate the overall charge on both sides of the equation. Okay, so let me jump out of the slides for a second and just do some examples so you can kind of see how all these steps work. Okay, so I think I'll do a few examples here. So let's say the initial reaction I'm given is silver plus copper makes silver plus copper 2 plus. So in this case, I can pretty easily identify the oxidation numbers. Everything's just an isolated ion or just a metal. So we know as it is, the silver is +1, copper is 0, silver is 0, and then copper 2 plus is +2, right? Metals in their standard state are going to be the same, are going to be 0, and then if it's an ion, the charge will just be whatever the charge on the ion is going to be. So if we look at what's happening, now we can say silver plus is being reduced and copper is being oxidized. And this doesn't change things all that much in terms of my balancing approach, but it helps us figure out what's going on. And it's got to be true that if one thing is being reduced, the other one's being oxidized, so that makes sense. So now I'm going to break it up into two half reactions. So on one side, I'll write copper makes copper 2 plus. Then on the other side, I'll write silver plus makes silver. So if we're following the plan for balancing, first it says make sure all atoms other than hydrogen and oxygen are balanced. That's fine. Then it says balance oxygen. There's no oxygen to balance. Then we balance hydrogen. There's no hydrogen to balance either. So then all we need to do is balance the electron count. That's the last step. So remember, what you're going to do is just add electrons to the more positive side to make the charges equal on both sides. So as it stands now, copper is 0 and +2, silver is +1 and 0. So in each case, I'm going to add electrons to the side that is more positive to get the charges to be equal. So for the copper reaction, that means copper makes copper 2 plus 2 electrons. And then on the other side, it will be the opposite, right? 1 electron plus silver plus makes silver. So at this point, each of my half reactions are balanced. But the important thing is I need the electron total from each half reaction to balance out. So since there are 2 electrons on the copper reaction, I'm going to need to consume those 2 electrons in the silver reaction. So to resolve that, I'll multiply the entire reaction through by 2. And so now I'll get 2 electrons plus 2 silver plus makes 2 silver metal. And so now there's 2 electrons out and 2 electrons in. And think about that as the last step in balancing all of this. So now finally what I'll do is just add them together. I think it's pretty clear what's going to happen, but just to illustrate exactly how we're going to approach this. We'll write out both reactions with their coefficients. And the entire purpose of this is it allows me to cancel the electrons out with the electrons in. And then I can write the final balanced equation as copper plus 2 silver plus makes copper 2 plus 2 silver. So we want to check two things, the atom count on both sides, as well as the charge on both sides. So the atom count looks good, right? It's 1 copper, 2 silvers, 2 silvers. For the charge, I've got +2 on the left side, right? There's 2 silvers, each one is +1. And I've got +2 on the right side from the copper 2 plus. So everything works out, and then this is my balanced equation. So that was probably one of the more straightforward examples for what we're thinking about here, because there wasn't any atomic balancing to do, there wasn't any hydrogen or oxygen to balance, so it's fairly straightforward. So we'll look at a slightly more complicated one next and see how that one goes. Okay, so this time, let's say my overall reaction is iron 2 plus manganese 4 oxide makes iron 3 plus manganese 2 plus. So if I want to, I can assign the oxidation numbers to everything, and then I can figure out what needs to be done. So let's do that. Iron 2, so we know that's +2. MnO2, so oxygen is -2 and there's 2 of them, so that makes the manganese +4. Iron 3, of course, is just +3, and then Mn2 plus is just +2. So again, you don't have to do this, but it'll help kind of strategize what's going on. So now I can say what this means is iron 2 plus is being oxidized, and Mn, I'm just going to say Mn4 plus is being reduced. So now I'm ready to break them into half reactions, so I can do that. I've got iron 2 plus makes iron 3 plus, and then a divider, and then MnO2 makes Mn2 plus. So I think I usually write the oxidation half reaction on the left side and the reduction half reaction on the right side. It doesn't matter, but just you want to split them up. Okay, so let's do the one on the left first. Remember, atoms other than hydrogen and oxygen, nothing to do for that. Hydrogen and oxygen, nothing to do there. Really, we can skip all the way to the charge balance, and we see what's going on, right? The iron is +2 on the left and +3 on the right. So in order to balance this, I'm just going to need to add an electron to the right-hand side. So it'll become iron 2 plus makes iron 3 plus 1 electron. Remember, the electrons are always going on the side that's more positive. We're adding negative charge to balance it out on both sides. So that's taken care of. Okay, the one on the right, we have a little bit more work to do because there are things to balance other than the charge. So first we say, do I need to balance anything that's not oxygen or hydrogen? No, there's 1 manganese on each side, so that's taken care of. Then the next question is, do I need to balance oxygen? And I do, right? There's 2 oxygens on the left, but none on the right. So what I'll do is add 2 water molecules to the right-hand side, and that balances out the oxygen, but it unbalances the hydrogen count. So now there are 4 hydrogens on the right and none on the left. So I correct that by adding 4 H pluses. And so now I'm balanced in terms of atoms, and now I need to get balanced in terms of charge. So at this point, I'll calculate the charge on each side. And it looks like it's plus 4 from the 4H pluses on the left side and just plus 2 on the right side. So that tells me what I need to do in order to complete the balance. Now I just need to add electrons on the more positive side. How many electrons? 2. Let me extend this line a little bit more. So now it becomes 2 electrons plus 4H plus MnO2 makes Mn2 plus 2 waters. So now charge is balanced in each half reaction, but what I want to do now is make sure that the electrons out from the oxidation match the electrons in for the reduction. And I can fix this by multiplying the oxidation half reaction by 2 so that it produces 2 electrons, which is what I need to consume in the other reaction. So this becomes 2Fe2 plus makes 2Fe3 plus 2 electrons. And now I can combine the two reactions together. So let me just rewrite them and we'll cross out as necessary. So this becomes 2 iron 2 plus makes 2 iron 3 plus 2 electrons. And the other reaction becomes 2 electrons plus 4H plus MnO2 makes Mn2 plus 2 waters. And after all of that, what I see is my electron balance is going to allow me to cancel them out on each side, and then I can write the overall reaction. It doesn't really matter the order you write your reaction, and usually I put the extra stuff like H plus and water on the ends, but it's totally up to you. So with that in mind, it would become 4H plus 2Fe2 plus MnO2 makes 2Fe3 plus Mn2 plus 2 waters. So at this point, I want to check that my atom count is equal on both sides and then check that my charge count is equal on both sides. So in terms of the atom count, it looks good. 4 hydrogens, 2 oxygens, 2 oxygens. So everything looks pretty good for that. And then manganese, there's 1 on each side. Iron, there are 2 on each side. So that's all balanced. So now we want to figure out the charges. So it's plus 4 from the 4H pluses. And then there's 2 Fe2 pluses. So that's another plus 4. MnO2 is neutral, so it's plus 8 overall on the left side. On the right side, I've got 2 irons times 3, so that's plus 6. And then another plus 2 from the Mn2 plus, and water is neutral, so that's also plus 8. So everything is balanced, so that looks like we've done everything that we need to do. Okay, let's do one more example, and then I think that should pretty much cover how to go about doing these balances. Okay, so this time, let's say that I have Cr2, try that again. Cr2O7 2 minus plus copper makes Cr3 plus copper 2 plus. So we'll start by figuring out our oxidation numbers. So in Cr2O7 2 minus, I've got a minus 14 from the 7 oxygens. And so that means the 2 chromiums need to add up to plus 12. And dividing by 2, I'll get a value of plus 6 for the chromium. The copper is 0. On the right side, the chromium is plus 3, and the copper is plus 2. So again, it doesn't matter all that much, but it'll help me to figure out everything else that I need to do overall as we go along. But now we can make a statement, and that's just to say copper is oxidized, and then chromium 6 is reduced. So either way, that sets me up to break them into half reactions. So copper makes copper 2 plus, and then Cr2O7 2 minus, it's the dichromate ion, makes Cr 3 plus. So as we do more of these, we can see that the one on the left is pretty straightforward, right? I just need to add 2 electrons to the left side, so it becomes copper makes copper 2 plus 2 electrons. On the right side, I kind of have a lot to do, though. The first thing that I notice is that the chromium count is not the same on both sides, right? That's where we want to start to make sure the total number of atoms are the same on both sides. So we're going to need to add a 2 on the right-hand side so the chromium count is the same. The next thing that we need to do is balance oxygen and hydrogen, and immediately we can see that there are 7 oxygens on the left and none on the right. So now it will be Cr2O7 2 minus makes 2 Cr 3 plus, and then I need to add 7 waters. So now that balances my oxygen, but it unbalances the hydrogen. So I'll fix that next by adding 14 H pluses on the left side. And so now I should be balanced in terms of atoms, including hydrogen and oxygen. So this should be the point where I determine the charges on each side to figure out how many total electrons I'm going to need for balance. So as it is now, I've got plus 14 and minus 2. So the left side of this half reaction is plus 12. And on the right side, I've got 2 times 3, so it's plus 6. So now, to finish off the balance here, it looks like I'm going to need 6 electrons on the left side. All right, let's see if I can fit this all here. 6 electrons plus 14H plus Cr2O7 2 minus makes 2 Cr 3 plus 7 waters. So 6 electrons from one half reaction, 2 electrons from the other, and I want to make these values match up. So I just really need to find the lowest common multiple. So for 2 and 6, we can both meet at 6, and I can achieve that by multiplying the entire copper oxidation half reaction by 3 to give me 3 copper makes 3 copper 2 plus 6 electrons. Okay, so now I'm ready to put these two half reactions together. So let's do that. Let's see. 3 copper makes 3 copper 2 plus 6 electrons. And then here, 6 electrons plus 14 protons plus Cr2O7 2 minus, the dichromate ion, makes 2 chromium 3 plus 7 waters. And here, all there is to do, like in the other two examples, is cross out the electron count from each one and then combine everything together. So 14 H plus 3 Cu plus dichromate makes 3 Cu 2 plus 2 chromium 3 plus 7 waters. So it looks like I've done my job. So now we just want to verify our charges on each side. So we can do that. So it's plus 14 and minus 2. So that's plus 12 overall. On the right side, I've got 3 coppers that are each plus 2, so that's plus 6. 2 chromiums that are each plus 3, that's also plus 6. Water is neutral, so now both sides are plus 12. I guess we should have verified the atom count as well, but it looks right. There's 14 hydrogens on each side, 3 coppers on each side, 2 chromiums on each side, and 7 oxygens on each side. So everything is pretty well balanced out. So that's the general strategy you want to follow for balancing these oxidation reduction reactions. I think I have one more example in the slides, so I'm going to jump back to that. Okay, so quickly I just have an example of balancing a reaction with permanganate and the oxalate ion. So this just breaks it down slide by slide and kind of shows each step as you're going along, so you might find that to be helpful. So we start by assigning our oxidation numbers to each element that's changing during the course of the process. So we figure out that it's manganese that's changing and carbon that's changing. Follow our usual protocol for doing that. I think this wandered, but the +4 is talking about the carbon, and we're basically calculating oxidation numbers knowing that oxygen is -2. So as we're going along here, we see manganese is getting reduced from +7 to +2, and carbon is getting oxidized from +3 to +4. So we're going to break up into our two reactions, and like I've been doing, we'll start with our oxidation half reaction, and the first thing we notice is that starting with step 1, are atoms other than oxygen and hydrogen balanced? No, there's 2 carbons on one side, but only 1 on the other side. So that's supposed to be in blue, but it's not standing out that well. So there's our 2 on the right-hand side to balance the atom count. Now we check to see if oxygen is balanced, and it is. There's 4 on both sides. That got balanced when we added the 2 to the right side. So then I have no more atom balancing to do. So then the last thing to do is to add 2 electrons to the product side, and now both sides are -2 charge, so we know that's all taken care of. Atoms balance, charge balance for each half reaction. So we'll leave that one for now and switch to the other half reaction. And here we have permanganate, MnO4- changing to Mn2+. So first we ask if there are atoms other than oxygen to balance. There are not, so we move on to balancing oxygen. There are 4 oxygens on the left and none on the right. So we balanced out oxygen by adding 4 waters to the right-hand side, but by doing that, we also unbalance the hydrogens. So we'll make up for that here by adding 8 hydrogens to the left side, right? It's 4H2O, so that's 8 hydrogens. So now we're balanced in terms of hydrogens. So lastly here, now that it's atomically balanced in this half reaction, we need to figure out the electron balance. So following our plan from before, we've got +8 and -1 on the left side, so that's +7 overall. And on the right side, all I've got is manganese 2+ with any charge, so +7 on the left, +2 on the right. So that tells me to add 5 electrons to the left side. So now I have my 2 half reactions, right? They're all fully balanced, 2 electrons from the oxidation, 5 electrons into the reduction. So this is the first time where we're going to need to multiply both reactions. So the top reaction we're going to have to multiply times 5, and the bottom reaction we're going to have to multiply times 2, so that we get 10 electrons in to the reduction, 10 electrons out from the oxidation. So we've got some multiplying to do and then some tidying up to do. So here's the top reaction after multiplying by 5, and then the bottom reaction after multiplying by 2. And again, our purpose for doing that is the electron count is even on both. When we combine it together, you see what we get. And then remember, we're going to cross out our electrons on each side. Nothing else is going to cancel out, but the electrons do. And then when we're all done, this is where we get our final balanced reaction. So all of the balancing that we've done so far has been in acidic solution, and that's usually the way we talk about doing it. But remember what I was saying earlier, that we could have acidic solution like in a car battery, but it would be a basic solution in a household battery. And so we could also balance under basic conditions. So there isn't really a strategy for balancing under basic conditions. Essentially, all you end up doing is following the protocol for balancing as if it occurred in acid. And then on paper, we flip things around by adding enough hydroxide to each side, to neutralize the H+. Once you do that, you're relying on the fact that H+ plus OH- makes water, so it'll get rid of all of the H pluses in our equation. But now you probably end up with water on both sides, so then at that point you might have to do some subtraction. So let me go back to our last example and switch it from an acidic balance to a basic balance by following this protocol. Okay, so we're going to use this reaction. I'm just going to copy it over to the top of the next page. So 14H plus 3 copper plus Cr2O7 2- makes 3 copper 2+ plus 2 that's not a plus sign, plus 2 chromium 3+ plus 7 waters. So now, according to the protocol for switching from an acid balance to a base balance, I'm going to add 14 hydroxide ions to both sides of the equation. Keeping in mind what we were just talking about, that H+ plus OH- makes water, that'll show me what's going to happen on the left side. On the right side, these 14 hydroxides have nothing to react with, so they're just going to be there. So now what I'm going to get is 14 H2O plus 3 copper plus dichromate. So the H plus is all gone. It reacted with the OH minus we added. And now it's all water. And on this side, 3 copper 2 plus 2 chromium 3 plus 7 waters plus 14 hydroxides. So on the right side, the copper, the chromium, and the hydroxide are going to stay. But you see now there's 7 waters on the right and 14 waters on the left. So we can simplify. 14 minus 7 is 7. So now it will become 7 waters plus 3 copper atoms plus 1 dichromate ion makes 3 copper 2 pluses plus 2 chromium 3 pluses. Water's gone now, but the hydroxide stays, so it becomes plus 14 OH minus. So that's how I would balance under basic conditions. And just for comparison, when we had it under acidic conditions, it was 14 H plus everything else the same. And 3 copper 2 plus 2 chromium 3 plus and plus 7 waters. So if you're kind of looking to see what happened, the water switches sides between acidic and basic, and the H plus on the left became hydroxide on the right. So that's really the protocol most people follow. If I have acidic and I want basic, I move water to the opposite side, and then however many H pluses I have on one side, I put that number of OH minuses on the other side. Okay, so the next thing that we want to talk about is how this works in application. So when we start on the next set, we'll start looking at how batteries actually work, and the technical term when we're talking about a battery is a voltaic cell. So let's stop for there and we'll pick up